refer to this picture, one that you may have seen in an earlier video that we've done. This is a bus architecture inside of a system. Our CPU at the top, and every place you see a black line, that refers to a bus. Now, some of the buses are very wide and very big and very fast, can move a lot of traffic, and I've got those marked as a wider picture. This front side bus, for instance, you'll see is a very dark line, a very wide and dark line. And that's because the front side bus in a computer is generally the fastest bus there is. And when you look at purchasing a new computer, you'll see in the technical specifications, they'll not only talk about what type of processor is in the system, but they'll talk about the speed of that front side bus, the megahertz or the gigahertz of that front side bus speed. And that's exactly what they're referring to, is how much traffic can we put across that front side bus? What speed is that running at? And if it's a 32-bit CPU, we have a 32-bit wide bus that is sending at a certain amount of megahertz. And that's what we're looking for speeds there on a system, because the faster that communication, the better it's going to be able to read and write to memory, and the better it's going to be able to read and write video out. And that's very often the most important things when thinking about the speed of a personal computer. And we also have these other buses that connect, for instance, between the North Bridge and the South Bridge. We have an internal bus, and there are buses for the PCI slots. There are buses for what we call a low pin count bus that goes to these slower systems like a serial port or a floppy drive or a keyboard or a mouse. You'll see a lot of about in this case is, I'll give you an example of how the South Bridge communicates over an 8-bit bus. Let's say we have this expansion slot in our system. And the way this bus works is we have this traffic that all travels in parallel in both directions up and down that bus. And the faster the bus speed, the faster that traffic will traverse. But you'll notice that it can't go more in the case of an 8-bit expansion slot. You can only send 8 bits at a time. You can't go any faster than that. So that's why we talk about that bus and the width and the speed being so very important. If it's a larger expansion bus, maybe we'll talk about 16-bit expansion cards. That means you can send 16 of the bits at the same time. And again, we've got this shared bus where the traffic's going back and forth to that, in this particular case, the South Bridge, and transferring that information back and forth. And that is how we get information back and forth out of those expansion slots into the South Bridge and ultimately up into memory and have the CPU work on.
Before. This is the board that uses a 8286 CPU, and you can here see the two different slots. This is the legacy original PC slot, and this is the extended, you can see the extension here, connector for the actual ISA slot, which is part of the ISA standard from 1984. So technically this is the only true ISA slot, but we refer to both as ISA slots and therefore ISA boards. So in this slide behind me here, you see the pinout of the ISA bus connector. This is the whole connector for the that is spec'd as part of the 286 computer, and this part here is the original PC connector, the 8-bit. You have 8 data bits on this connector, and you have another 8 on this. So in total, you have 16 for the whole interface. Here on this next slide, you'll see a motherboard with 4 PCI Express slots, and you can compare those with the 4 older ISA slots right here. And this one is a Pentium motherboard. Here is a slide that describes the overall architecture of the PCI bus in the system. And the key thing to note here is that you have a bridge chip between the processor and the local bus, the PCI local bus. It's actually a little bit of a misnomer here in this picture to call it a local bus because it's not actually local. Local buses should be attached to a processor, but it's a PCI bus. The way the bridge works is that the operating system configures the bridge to map a portion of the processor's address space to PCI address space. These two address spaces are completely separate. If the processor then, by using a device driver for the device that is being accessed, accesses a register that the bridge recognizes as being mapped to a graphics card or another card here, then the bridge would claim that primary bus transaction, the memory bus transaction, and create a secondary transaction on the PCI local bus. That secondary transaction would then be claimed by the graphics card here, for instance. The graphics card would do the read or write or whatever transaction is being performed. Could be I/O too. And then the transaction would complete on the secondary bus, on the PCI bus. The bridge would then complete the primary bus. So it works as a bus master, if you will, on the PCI bus on behalf of the processor. This slide shows the PCI bus interface signals. There are two groups of signals. One is the required pins group and one is the optional pins group. So let's start with what's optional. What is optional is to implement the 64-bit parts of the signal, so that if your device is a 32-bit device, only lives in the lower 32 bits of the address space, for instance, then it does not need to implement these signals. Also, you don't need to have interrupt support if your device is, for example, a polling device that does not interrupt. You don't need those. And also, you don't need the JTAG signals. What you do need is the address and data signals to get the address assigned to the device and the data in or out. You need command byte enable. The byte enable signals are used for reading or writing individual bytes. So you might want to write the first 2 bytes, but not all 4 bytes in a 32-bit D word. You have a parity signal, so that parity can be checked. If there's something wrong with the parity, you would report that to the operating system or the other side, rather, depending on who's reading and writing, using the parity error signal. If there's something else wrong, critically wrong, you can assert the system error signal, in which case the system would basically bug check and lock up, if not handled in any other way. You have request grant for bus mastering. You have clock and reset signals. And this is pretty much everything needed to implement a PCI compliant device. This slide shows the configuration space registers. On PCI, you actually have 3 unique address spaces that can be used. The first 2 are the normal memory and I/O address spaces, which are used for accessing registers within the device that are related to your the operation of a device. The third address range on PCI is the configuration space. The configuration space registers are used by the operating system to learn about the capabilities of the device and what resources the device needs to do its work. So I'm going to go through the various registers behind me and give you an overview what they are used for. The most important registers are the vendor ID register, the device ID, and the base address registers, or also called bars. The vendor and device ID registers are used for plug-and-play purposes. The operating system goes and reads these 2 registers on all devices to learn the manufacturer and what type of device it is, and based on that information it would match that with a device driver that will configure the card. The base address registers are used for letting the operating system know what memory and I/O ranges are needed by the card to do its work. So how this works is that the operating system reads the type and size required for each register bank. You might, for instance, have 4 kilobytes of I/O space, and you might have another 8 kilobytes of memory mapped space that the card needs to do its work. So the operating system goes and reads the size of it and determines a location within the overall memory space of the system, and then writes that the base of that address, and that's why it's called base address registers, the base of the start of that range within the system memory, writes it in those registers, and therefore
what's known as the motherboard. The motherboard allows all the components in the computer to connect to each other. So we'll flip the CPU back over and plug it into the motherboard. On the right of the motherboard is a place for something called RAM. RAM is short for Random Access Memory, and it just contains all the data that is being processed by the CPU. Let's learn a little bit more about RAM by looking at how the CPU and RAM interact. For now, we'll remove the wires on the left and move the motherboard over to make room for the RAM chip. RAM consists of a list of addresses, and at each of those addresses is a piece of data. The CPU normally requests and processes each piece of data from RAM in order, one after the other. However, if the CPU is instructed to pull data out of order, it can do so. That is why it's called Random Access Memory. The data can be accessed randomly if it needs to be, although normally it's accessed in order. When the computer first starts running a program, it sends an address to RAM to begin retrieving that program. The RAM address just consists of a series of ones and zeros representing on and off wires. RAM doesn't do anything with that address, though, until the CPU also turns on the set or the enable wire. If the enable wire is turned on, RAM automatically sends whatever piece of data is at that address back to the CPU. That data is then processed by the CPU accordingly. Once the CPU is finished processing that piece of data, it then sends another address to RAM, turns on the enable wire, and gets the next piece of data from RAM. This process happens over and over again inside the computer. If the CPU needs to save data to RAM, it outputs an address, outputs some data, and then turns on the set wire. The RAM will then overwrite the data at that address with the new data. But what is that data inside RAM? Because it just looks like a bunch of ones and zeros. Well, it's made up of different things. Some of the most important pieces of data in RAM are the instructions. Instructions just tell the CPU to do different things. There are also numbers inside that data. These are numbers that you might want to add together, compare, or simply process in some way. Another thing, and this is kind of weird, that is in the data is addresses. At particular memory addresses in RAM, the data itself is also an address. These addresses can be used for various things. For instance, if you want to output a number to an external device, you have to know the address of that particular device. Do you want to send data to the printer, or do you want to send it to the monitor, for instance? There are also letters stored in RAM. If you want to show some text on the screen, you would actually store it as a bunch of ones and zeros in RAM. Each letter is stored as a particular combination of ones and zeros according to a character code. These character codes are arbitrary. Someone just decided that this is a lowercase a and this is an uppercase G, for instance. So that's what's actually in the data inside RAM. Now let's go back to seeing the data as just a bunch of ones and zeros. And we'll now move the RAM chip into the RAM socket on the motherboard. We'll then group the RAM addresses and data together.
In Section 1, we talked about secondary memory, which is permanent storage. This dealt with hard drives. Now we'll talk about primary memory, or temporary storage. This is called RAM. RAM stands for Random Access Memory. In order for data or a program to run, it needs to be loaded into RAM first. So here is how it works. The data or program is stored on the hard drive. Then from the hard drive, it is loaded into RAM. And once it's loaded into RAM, the CPU can now access the data or run the program. Now, a lot of times, if the memory is too low, it might not be able to hold all the data that the CPU needs. And when this happens, then some of the data has to be kept on the hard drive to compensate for low memory. So instead of data going from RAM to the CPU, it has to do extra work by going back to the hard drive. And when this happens, it slows down the computer. So to solve this problem, all you need to do is increase the amount of RAM on the computer. And by increasing the memory, all the data can be loaded into RAM without the need of constantly accessing the hard drive. And the result is a faster performing computer. RAM requires constant electrical power to store data, and if the power is turned off, then the data is erased. RAM is stored on the motherboard in modules called DIMMs. These DIMMs come in different memory sizes. Today, they range anywhere from 128 megs to 4 gigs of memory per DIMM or more. RAM also comes in different types, such as dynamic RAM or DRAM. DRAM is memory that contains capacitors, and because it has capacitors, it has to be refreshed often. SRAM stands for synchronous RAM. This memory uses transistors and does not have to be refreshed, unlike DRAM. And because of this, it is much faster than DRAM, and it is also very expensive. An example of SRAM would be the memory cache level 1 and 2 that is used by the CPU. Another type of memory is called SDRAM, which stands for synchronous DRAM. This type of memory is what is used today in RAM DIMMs. The difference between SDRAM and DRAM is basically speed. The older DRAM technology operates asynchronously with the system clock, which basically means that it runs slower than the system clock because its signals are not coordinated with it. But SDRAM runs in sync with the system clock, which is why it is faster than DRAM. All the signals are tied to the system clock for a better controlled timing. SDRAM is rated at different speeds. For example, a stick of SDRAM could be labeled PC100. The 100 equals the speed at which it operates, which is 100 megahertz. And since SDRAM only comes in 64-bit modules, it has an 8-byte wide bus, because 64 divided by 8 equals 8. So to figure out the total bandwidth of PC100, you multiply 100 megahertz times 8 bytes, which equals 800 megabytes per second. So the total bandwidth of PC100 equals 800 megabytes per second. So an SDRAM module labeled PC133, you multiply 133 by 8 bytes, which equals 1066. So the total bandwidth for PC133 equals 1066 megabytes per second. As technology increased and processor and bus speeds have gotten faster, a new RAM technology was developed to keep up with the faster speeds of computers. This newer technology was called DDR, which stands for double data rate. And that's basically what DDR does. It sends double the amount of data in each clock signal when compared to non-DDR RAM. Non-DDR or single data rate RAM uses only the rising edge of the signal to transfer data. But DDR uses both the rising and falling edges of the clock signal to send data, which makes DDR twice as fast. DDR is also labeled differently than non-DDR RAM. Instead of including the clock speed in its name, like PC133, where 133 equals the clock speed, DDR uses the total bandwidth instead. For example, a DDR DIMM labeled PC2700, the 2700 is not the clock speed, but it's the actual total bandwidth. The clock speed for PC2700 is 333 megahertz. So 333 megahertz times 8 bytes is rounded off to 2700 megabytes per second, which is where we get the name PC2700. Another example is PC3200. PC3200 has a clock speed of 400 megahertz, so 400 times 8 equals 3200, which is where we get the name PC3200. A new technology that has succeeded DDR is DDR2. DDR2 is faster than DDR because it allows for higher bus speeds, and it also uses less power than DDR. A DDR2 DIMM has 240 pins, compared to 184 pins on DDR. Some examples of DDR2 are PC2 3200 and PC2 4200. And the latest RAM technology is called DDR3. DDR3 is twice as fast as DDR2, with a bandwidth of over 12,800 megabytes per second. Like DDR2, a DDR3 DIMM also has 240 pins, but the notches in the DIMMs are in different places. So you can't put a DDR3 DIMM in a RAM slot made for DDR2. In fact, motherboards are made to support a certain type of memory, so you can't mix DDR1, 2, or 3 on the same motherboard. Some examples of DDR3 are PC3 8500 and PC3 12800. Another type of memory was called RDRAM, which was developed by Rambus Inc. And they developed the RIM, which stands for Rambus Inline Memory Module. RIMs have 184 pins and look similar to DIMMs, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. When RDRAM debuted in 1999, it ran at 800 megahertz, which was considerably faster than SDRAM, which ran at 133 megahertz at that time. But even though it was a lot faster than SDRAM, RDRAM only had a 2-byte wide bus, compared to SDRAM, which had an 8-byte wide bus. So if you multiply the speed of RDRAM, which was 800 megahertz, times the bus width, which was 2 bytes, you will get a total bandwidth of 1600 megabytes per second.